right, so electric fields and field intensity. Just make sure that I'm on board with my own lesson. Shuffling the papers. So I'm going to do this like more old-fashioned with just paper, no slideshow or anything like that. When we're talking about a field really gives rise to a property of space. And it's a hard thing to picture because those fields are going to be invisible. Just like gravitational fields are invisible, but we don't have any doubt about the existence of a gravitational field. We just know that if you're in proximity to a planet, you know that there's going to be some sort of a field, a gravitational field pointing towards that planet. And we take it for granted because we kind of believe in gravitational fields because we've been learning about them since we were little. So like, if you take a golf ball and you drop it, you take a golf ball, like you hold it up in the air and it falls from the air. Nobody's shocked at all, but these gravitational field lines point towards the center of that planet. And we're all good with that. So we know that these fields affect the space around the object. And we don't think that there's like matter projected out into space. We know that the matter, the planet in this case, is affecting space somehow. Somehow it's causing space to have sort of an invisible slopiness to it. It's going to cause things to roll downhill, if you like, towards that thing. And it's hard to think of it as rolling downhill towards that thing because it's a volumetric phenomenon, right? We're in 3D. But if you think of it as like a gradient or a hill, things rolling towards the mass, I can kind of believe in that, like sort of as an analogy. So it's truly the idea of action at a distance. And when I have a mass like Earth, it's exerting a force on other masses that find themselves in the presence of that gravitational field. So there's that action at a distance effect, or we could say exerting a force without touching. And that's what we believe in with gravity. And, it's important to believe in that as well for electric fields and electric charges. So this idea of field intensity, it's just it sounds like I'm saying the same thing twice, but field intensity is simply the intensity of a field, which sounds like a silly way to define it, but how strong the field is. Like if it was a hill, how slopey the hill is. But it's not a hill, it's a field. But hill is a nice way to picture it, a slopey hill. It's got a lot of hill intensity, right? An electric field would have a lot of field intensity. And we can describe this using a mathematical model. So we have this model of electric field intensity. And of course, it also has an orientation. We use the Greek letter epsilon, which looks like a curly capital E. And one of the reasons we're using curly capital E or epsilon, Greek letter epsilon, is because capital E, just like big old capital E like this has already been used for energy so much. We're going to use epsilon for our electric field. And you notice that I put a vector over top of it because while energy is a scalar, electric fields, of course, are vectors. So we're going to sort of roll with that. And we could also say that electric field is defined as the force divided by the amount of charge that's in that field. And maybe I should say that a little bit better. The force that's felt by a test charge is equal to the strength of the electric field. And when I say a test charge, maybe I could go back to my gravitational model. If I have a planet, and this planet has a ton of mass, and I have this little satellite or something that has a little bitty mass, it doesn't shock me at all to say that the gravitational field of the planet totally outstrips the strength of the gravitational field around the satellite. Like the gravitational field around the planet dominates. It's the dominating effect for producing a gravitational field in this region of space. That little satellite we might call the test mass. We could use it to test how strong the gravitational field is. In the same way that if I picked up a golf ball and I dropped it, it wouldn't be shocking to know that it's going to fall towards the Earth, but I could use it just to test the gravitational field strength. And that would, I would test and I would observe what the acceleration of that golf ball is, and that would be my way of figuring this out. With this test charge, we could test the electric field intensity by observing how much force would be exerted on that test charge, in the same way that we could check the gravitational field intensity by checking how much force is exerted on a test mass. So that's my analogy, okay? I think it stands up pretty good so far. The next thing is where the force is the force. Wow, that sounds a little bit repetitive. Where the force is the force due to a charge, and the field strength can be determined by feeling, that's that force bit, the force exerted on a test charge in a field, and then dividing the test charge by its magnitude. And that's just describing what that equation says. And before I go any further, I want to talk about electric field lines. So things But the conventions for electric field lines, and Quinn was asking about this earlier, like, is it arbitrary? Is it something that had like a rationale? And I had to admit that I don't know the trivia behind the rationale, but I will show you the pattern, right? Just in case you missed it. If I have a negative charge, the convention is that electric fields orient towards negative charges. And if I have a positive charge, then the convention is that I have electric fields orienting away from positive charges. So that's the convention. And I don't have a great analog for this with masses, because really I only have one type of mass. Call it positive mass if you like. I don't have negative mass and positive mass. If I had negative mass and positive mass, then I suppose one's gravitational field would orient away from the mass, and one would have a gravitational field that orients towards the mass. And since I don't have those two kinds of masses, I only have the one kind of mass, I can't make this kind of analog with mass. Are you picking up what I'm putting down? Like, I don't have negative mass or opposite mass, whatever that is. It's just not something that is on my radar as a thing. And if it comes out that there's like some papers that get written later on and we realize, oh, there really is this thing called negative mass, which has oppositely operating gravitational fields, then I'll stand corrected, and that'll be cool, and I'll be happy to be corrected. So begins on the positives, ends on the negatives, or orients away from the positives and towards the negatives. And the question often is, what happens if I have a positive charge and a negative charge that come near each other? So if I have a positive charge, actually, let's just do two positive charges. What the heck? Two positive charges near each other. And if you have space on your page to write this, then by all means do. But if I have two positive charges that are beside each other, then I could say, hey, maybe I'll do it in colors. If I have a field that's going outwards from this positive charge in all directions, and that's red, so maybe blue. And I have field that's going out in all directions from this charge. I mean, if these two charges didn't know about each other, we could say, oh, look, these two charges are just happy beside each other, and they're sending out fields in all directions, and they happen to cross at that one point. But I've kind of alluded to the idea that we could think of fields as kind of like a slopiness to space. And I think we kind of know that, except for those like olden time stories where parents tell us about how they had to walk uphill both ways to school, you can't have a hill that slopes upwards and downwards at the same location in space. That doesn't make physical sense. That's just not a thing. You can't have an upward facing hill and a downward facing hill at the same point in space. And the same thing is true for gradients with fields. When we talk about the orientation of an electric field, you couldn't have an electric field that goes like up and to the left and up and to the right at the same point in time. In fact, what I would do is I'd say, hey, look, maybe I'll just zoom down here a little bit. If I did have a field that went this way and this way at the same spot, if there were two charges, we take up this idea of superposition. We talk about the superposition of these fields. They can't both be true. So let's see what happens if we superimpose them on top of each other. And it really is a vector addition thing where I've got a y component. Maybe I could call this epsilon due to charge 2. This is epsilon due to charge 1. I'd have a y component and an x component. I could call it epsilon 2x, and I could have, I've left myself like no space here, epsilon 2y. And then I'd also have like epsilon 1y and epsilon 2y. So 1x and epsilon 1y. And as I look at this, look at the x's. See how they're opposite to each other? These x's are going to sort of cancel each other out, right? But you notice the y components are in the same direction, which means that when I have these two charges that are side by side, I didn't mean to take that out of your way. When I have these two charges that are side by side, what effectively happens is when I have a positive charge and another positive charge, sure, we could talk about the electric fields. Maybe I'll go more color-coded again. Electric fields orienting like this away. But when we talk about how they would cross over, people typically will do this kind of, like, I don't want to use the word asymptote, because it gives a wrong idea. But can you see that they sort of look like they splay off of each other? And the reason I don't want to use the word asymptote is because that's really not at all what's happening. First of all, it's on a graph. But secondly, there's not like zero electric field in this, what I've just called an asymptote. Really, there's like an intensified Y electric field, intensified electric field pointing in the Y direction, downwards and upwards. In fact, the only place where there's zero electric field would be a point right in the middle, right where that dot is. And the reason that would be the case, if I go back to my first diagram, can you see that there's all X components and no Y components? And the X components could cancel each other out. But since there's no Y components, there's no like vertical component to this field, we could say that there's a point between them, like along a line connecting the two, where there could be zero electric field. That could be a thing. Okay, so we'll talk about that. But that's a possibility. But there's definitely not zero electric field up in these upper and lower regions, which I kind of called an asymptote, but I feel like it's dirty to say that because zero means that it doesn't approach zero, but it just means like it splays off, right? Is it okay if I take this away? Okay, take this one away. So we don't have two different orientations simultaneously. We have to use the idea of superposition to figure out what the field is at a particular point. But back over to this, we've got a little statement here that the number of lines per area is, in our drawings at least, is a visual indication of the field intensity. Now there isn't like a physical line there, right? Like when we talk about electric field lines, it's not like this thing that like you could grab onto it and you can point and say, oh, there it is, that's the field line. In real space, like if this golf ball was charged, I couldn't like point to a spot and say, there's that field line, there's that field line. Like it's just a concept, right? It's a construct for thinking about intensities. But in our diagrams, the closeness of the field lines indicates intensity. And we already established this idea that field lines can't cross, so we talk about superposition. Or we can talk about summation, just adding what the different vectors would be for those epsilon, those electric fields. We can add them up as vectors. And then I just want to throw out this idea of Coulomb's law. So Coulomb's law says F is equal to K times Q. I'm just going to say Q1 for charge 1, but then I used the idea of Q test before. Let's just say that Q1 is like the dominant charge that's, making the big electric field. And I have Q test, like this little bitty charge that comes nearby. So I'm not going to call it Q1 and Q2, I'll call it Q1 and Q test. And they're separated by a distance R. You got that R squared for Coulomb's law. We can call this Fe if you want to for electrostatic force. But then if I say, hey, I'd like to take that equation and sub it into our earlier epsilon equation, maybe 4 should have a vector on it too. The earlier vector equation for epsilon was F over Q test. And if I sub those guys into each other, Fe goes in here as Fe. You notice that there's a Q test in the numerator and a Q test in the denominator. And so what happens is we end up getting epsilon equals K times Q1. And I'll leave it as absolute value of Q1 because this would be the magnitude of epsilon. We could figure out what the orientation is later on based on whether it's a positive Q or a negative Q. But epsilon is equal to KQ1 over R squared, where R now would be the distance that you are away from that charge. So that if I have a charge, Q1, and I'm a certain distance away, R, then I can calculate what the epsilon is at that point in space. And if it's a positive charge, Q1, then the epsilon would be away. And if it's a negative Q1, then the epsilon would be toward the original field-giving charge. Okay, so that's a matter of the field conventions, what the orientation would be. Maybe I should pause. Anybody have any questions?
And that's in newtons per coulomb?
Oh yes, yeah, units are still newtons per coulomb. And we could figure out what the newtons per coulomb, or that the units are newtons per coulomb by sorting ourselves through this K constant up here, newtons per coulomb, or we could go back up to this simpler equation and say, all right, well, units are going to be newtons for the force and coulombs for the charge. So newtons per coulomb, is the unit for epsilon, for the electric field. Any other questions? That's a good one. Sorry, I skipped over the units. Yes, sir.
How come we can cancel out the second charge for like electric fields, but we can't cancel out the second mass with gravity?
Oh, that's interesting. So if we wanted to make that analogy to gravity, so with gravity, if we said Fg is equal to G mm, where big M is like the big mass, right? And little m is the little mass, divided by r squared. If I wanted to say that the gravitational field intensity is equal to F big G over the little mass, that actually does work out. What we'd be doing then is saying G m over r squared, all divided by little m. The m's do cancel out, and we could say that G is equal to gm over r squared. That actually is a valid statement.
Okay.
I mean, sometimes we calculate it that way too. We totally could do that. Yep. Yeah, that's a good question. So yeah, the analogy holds up in that case. Analogies don't always hold up, but in this case it does. Okay? With positive and negative charges, I struggle because there's no positive and negative masses. Let's take a look at this question here. So, oh, sorry, yeah, another question.
If you are using, if it was like an actual sphere of charge, let's say, around with them, what would that look like when they're, like, would it just kind of squish like you're pressing two balls together?
So if you had a sphere of charges,
well, it's like you had like the two charged objects and you tried to squish them together.
Oh, if you had two like charged objects and you tried to push them together, I think the easiest thing that maybe we've experienced since childhood is playing with magnets. And if you take two norths and you try to push them together, then I know that's obviously a magnetic field, not an electric field,
Yeah.
but that's something that, you know, like tactile wise, you've probably experienced, right? It's going to be a force field that's going to resist that push. It's kind of like a field-based cushion, right? Yeah. So, I mean, with magnets, I know magnets are not the same as electric fields, but at least, again, it's an analogy to give us a feel for what that would be like if we tried to push things together. Yeah. Well, let's take a look at these guys. So I've got two charges, Q1. I'm going to label this one as Q1. This one is Q2. So I've got two charges, and I'll start giving my givens. Q1 is equal to even the stupendously huge charge of 2.0 coulombs, which actually is really big, right? And Q2, negative 3.0 coulombs. And it says that they're separated by a distance of 5 meters, but we want to investigate a point that's midway between them. So at a point midway between, I would say, all right, well, R1 is equal to 2.5 meters, and R2 would also be equal to 2.5 meters. So at a point in between, what's the electric field going to be equal to? You know, as I look at this, I say, well, first of all, Q1 is a positive charge, and what we've said previously with field conventions is that the electric field due to a positive charge points, do you remember, away from or towards that charge? Away, yeah. So, you know, I'm going to label this out. This is just a part of my thought process, and it should be a part of your thought process too. I would say, all right, so epsilon 1 is going to go that way, away from the positive charge. And again, as I think this through, now I'm going to go over to charge 2 and say, what's the convention? Electric fields go away from or towards negative charges. I saw somebody mouth it. Thank you, Aaron. Toward, yeah. So I got epsilon 2 going to go towards. Okay, so in this case, I've got both of these fields due to the positive and negative charges at that point in space would both be oriented towards the right. And I think just for simplicity, let's make to the right be positive then and to the left be negative for our reference frame. Because since this is a vector scenario, I gotta come up with a reference frame because directionality matters for us. So if we want to figure out what the electric field would be at that point in space due to these two charges, I'd say, okay, well, the sum of all the electric fields, and you might see this sigma summation notation, or we could say epsilon total, but they mean the same thing for us, is going to be epsilon 1 plus epsilon 2. And in this case, I don't have to deal with positives and negatives from the reference frame because both of them are positive. And so it's very simple to sort of handle that. So as I expand these guys out, I'm going to make use of that equation that I stated earlier, K times absolute value of Q1 over R1 squared plus K absolute value of Q2 over R2 squared. And I've already dealt with the positive signs for the reference frame. I could just start subbing things in here. Now, the lazy person that I am, I think I would probably factor the k's out so that I only have to type in the scientific notation once. So I'm going to do that, and I'm giving, I'm voicing that I'm doing that, because sometimes when you look up the solutions in the textbook, you wonder, what is this witchcraft and wizardry that's happened here, and why is that k all by itself? I'm telling you, that's what people commonly do, okay, because it's a common factor. So I'd say, okay, 8.99 times 10 to the power of 9 Newton meters squared per Coulomb squared. And I'm going to need some people with calculators to help a fella out with this one. And I'll put in my Q1 and my Q2, so 2.0 coulombs over R1 squared, which was 2.5 meters squared, plus 3.0 coulombs. And you notice that I'm already doing my absolute values as I'm subbing these in, because I've dealt with the directionality from the reference frame already. 2.5 meters squared, bracket that guy off. And I'm going to ask, if you're watching this video remotely, actually try and solve this, type it into your calculator, because being able to do the scientific notation is something you need to be able to do. But if you're doing it live with me, actually do it. Use your calculator. Make sure that you can make this go in, and I want to hear some answers. Yeah, that's cool. Greg, did you get it already? Where'd you get?
7.192 times 10 to the 9.
I love it. 7.192 times 10 to the power of 9 newtons per coulomb.
I can verify that as well.
All right, the motion passes. And of course, we would round that off. Don't tell the math teachers 2 equal signs on the same line, but I've run out of space. So we'll round that off to, did we only have 2 sig figs? What a crime. 7.2 times 10 to the power of 9 newtons per coulomb. Okay, so this is like a nice one-dimensional problem. And if I was talking as a chemistry teacher, can you see that it's a dipole? So chemistry people might talk about this as a dipole scenario. That just means we have, a linear configuration with a positive on one end and the negative on the other end. But that's not how we're dressing this one up. We're just addressing it as a field problem, right? So nice to see that there might be some crossover with chem as well. Yep. All right, can I flip over this page? Cool. And I know Mrs. Killens would have a fit if she knew that I wasn't going to break up this video. It's going to be one great big long video, because she likes it when I break up videos into 10-minute segments, because she complains about the attention span of children today. So if you're watching the video, pause it, go pee, and come back again. I mean, take a break and come back again, okay? People in class have to endure it live. All right, back. Example 2. Sorry for the break, people that are live, because you're not all going to go to the washroom. Ha ha ha. All right, so back over to this one. We're going to go with the more realistic scenario of microcoulombs. This time I've got 2 negative charges, and they're in microcoulombs, so we're going to sort of deal with that. We've got charge 1, charge 2, Q1, and really which one is 1 and which one is 2 is a little bit arbitrary. I'm just reading from left to right, because that makes sense. But if somebody becomes really explicit about which one is charge 1 and which one is charge 2, just roll with it. So Q1 would be negative 1.0 microcoulombs, and I'm going to translate to coulombs automatically. I'm on autopilot here. So 1.0 times 10 to the power of negative 6 coulombs, and Q2 is going to be negative 3.0 times 10 to the power of negative 6 coulombs. And it says they're separated not by 5 meters this time, but by the slightly more realistic value of 0.5 meters. So we'll say that R1 is equal to 0.25 meters, and R2 is equal to 0.25 meters. Just to scale it down a little bit, right? Because we're probably not doing 5 meter long experiments. Maybe 0.25 meters, it's less than a meter stick. That's reasonable. All right, so we've got our physical setup here. Oh, before we go any further, we should take a look at the orientation of the electric fields. So again, I got 2 negative charges this time, so maybe it'll be a little bit different. We said before that electric fields orient towards negative charges. So I could say, all right, I've got my epsilon 2 orienting towards charge 2, and epsilon 1 is going to orient toward charge 1. And again, as I'm thinking out how to approach this problem, I'm going to look at the asymmetry in this. Take a look at charge 2. See how it's like triple charge 1? It's bigger, right? That tells me that charge 2 is probably going to dominate this scenario, just a little bit, just because it's 3 times bigger. So I think that I'm going to make to the right be positive, not because I want to be the same as last time, but because based on my situation, it looks like to the right is going to be, the dominating vector here. So I've got a picture to help me to sort things out. I've got a reference frame here to help me with my positive and negative signs. And now I'm going to go back to my equation approach. So, okay, epsilon total, summation of fields, epsilon total, depending on how you're writing it, is going to be equal to epsilon 1 plus epsilon 2. Electric field 1 plus electric field 2. And at this point, I might want to introduce my negative signs from reference frame. And I look at epsilon 1. Epsilon 1 is pointing towards the left, so I think I'm going to insert that reference frame negative sign now, keeping in mind that both charges are negative. So that negative sign is because of the reference frame, not because of the charges. I mean, I guess it isn't directly because of the charges, because the direction of the field is going to dictate the orientation of dictated by the charge. But anyway. So we're going to expand out that epsilon 1, so k times q1, absolute values, divided by r1 squared, plus k times q2 divided by r2 squared. And then as I'm looking at this, I could factor out the k's. In fact, because of the symmetry of this problem, I could even factor out the r's, because r1 and r2 are the same value. But just for argument's sake, because it's not always symmetrical, I'm not going to do that. I'm only going to factor out the k's, just because the r's are not always the same. So I'll say, all right, so negative, actually, let me just do positive k. No, I'll do negative k, because sometimes the textbook solutions does this. So let me point that out. I'll do negative k times q1 over r1 squared, minus, see how the negative would multiply through the brackets to make it become a positive on the second term? Q2 over R2 squared. Just pointing out, sometimes if you see this in solutions, negative times the first term makes it negative, like I said before. Negative times the second term turns it positive. And again, this is one of those magical mystery things that people see in solution manuals. And I want to make sure that you see why that's the case, because otherwise it might not pop for everybody, right? Anyway, I'm going to start subbing in my values, and when I sub in my values, epsilon equals negative 8.99 times 10 to the power of 9 Newton meters per Coulomb. Yeah, I wrote it right, even if I didn't say it right. Times, and now I got to sub in those values, and I think I might run out of space because of my paper here. So 1.0 times 10 to the negative 6 coulombs. Notice I've already done the absolute values over 0.25 meters squared. Minus is going to be on the second term, because remember, minus times minus is positive. 3.0 times 10 to the negative 6 coulombs over 0.25 meters squared. Close off those brackets. And I did this one earlier, and I only wrote down the rounded value. So I wrote down 2.9 times 10 to the power of 5 newtons per coulomb. Is there anybody is much faster than me that has an unrounded value?
2.8800 newtons per coulomb.
2.88?
That's what I know.
0?
2.88000.
All right.
Sorry, 2.8768.
7.6? All right. 7.68?
7680.
All right, I'll leave it there then. Anyway, it just confirms that we got it right anyway, right? Times 10 to the power of 5 newtons per coulomb. So that's nice. That's a nice feeling.
Sorry, I did my math yesterday with 9.00, because that's what was in the last.
Oh yeah, the 9.00 versus the 8.99. So yeah, if you're doing a test or an evaluation, just make sure which K value are we going with here? Is it like the textbook version or some other less rounded version, 8.99 times 10 to the power of 9. And it just sort of like ensures we get the 3 sig figs there in the end anyway. But then I knocked it down to 2 sig figs with the givens. All right, I want to take a look at a two-dimensional problem. So we got this equilateral triangle. And we've looked at this symmetry problem like this before in 2D, but look at it again. We've got two charges here. I'm going to call this charge 1 and this charge 2. And a typical way to talk about a point in space is to just label it with a P. P is for point in space. Okay, so this P stands for a point. And just like there would be 60 degrees in any equilateral triangle like this, the top angle would be 60 degrees. But if we're trying to figure out what's going to happen with the electric field at this point, notice that each of these charges is negative. So the electric field due to charge 2 would point this way down that edge toward the charge. Epsilon 1 would be down that edge. So I've got my epsilon 2, I've got my epsilon 1, sort of down and to the right and down to the left. And I have this angle in between them. Of course, that angle is 60 degrees, but maybe I'll just like sketch it over here. Here's point P. This makes me feel a little bit like a free body diagram, but it's really not a free body diagram because I'm not talking about forces on a mass. I'm talking about electric fields that are occurring at a point, right? So these two arrows represent the electric field at point P. It's a little bit abstract, I get that. So epsilon 2, epsilon 1. If the total angle is 60 degrees, then if I'm going to reduce these guys down to right angle triangles, then I'm going to have an epsilon 1y and an epsilon 2y where the angles would be 30 degrees, right? Because 60 degrees divided by 2. So up at the top of each of these right angle triangles would be a 30 degree. And I'd have epsilon 2x and epsilon 1x. So the reason we're going to break it up into two right angle triangles is so that we can approach this with like a SOHCAHTOA trigonometry mentality, similar to the way we would do like a tension problem or something like that if we were like pulling on an object, but it's not forces anymore, it's electric fields. And we just want to figure out what the electric field would be at that point. So one thing that we could do is set this up as epsilon total in the x direction. And if I want to talk about epsilon total in the x direction, summation notation would look like this. Epsilon x total. So we'd say, all right, so that would be epsilon 1x plus epsilon 2x. As I look at it, I see that epsilon 1x and 2x are in opposite directions. So I might give myself a reference frame like this. And for lack of a better reference frame, I'm just going to call it north, south, east, and west. And I would probably call south the positive and north the negative because things are kind of going south here. And again, just because I'm not creative, east positive and west negative. And I can see that epsilon 1x and epsilon 2x are going to have opposite signs. So I think I'm going to insert a negative sign in front of epsilon 1x just to make use of that reference frame. And I could start expanding things out. I could say, okay, negative k times q1 over r1 squared times, and now I got to ask myself in the x direction, would that be sine theta or cosine theta?
In x, it would be sine theta.
Sine theta, yeah. And if I wanted to be really picky about this, I could say it's sine theta 1, just in case there wasn't symmetry there, right? But there is in this case. So this is the same theta. Plus k times q2 over r2 squared times sine theta 2. And again, the 1 and the 2 on the thetas is just a little extra, just in case it wasn't symmetrical, but it is. And as I sort of do a little inspection here, I think to myself, well, wait a minute, k's are the same k, because it just would be. Q1 and Q2 are the same because that's just the case this time. R1 and R2 are the same because it's an equilateral triangle, and the length of each side is 3 meters. So the R's are going to be the same. And theta 1 and theta 2, again, because it's symmetrical, they're the same. So essentially I have like negative of some value and positive of the exact same value. So a common way to sort of deal with this is to just say E total in the, or epsilon total in the x direction is equal to 0 newtons per Coulomb by symmetry inspection. Well, let's just save ourselves some time and not sub in all those ugly values.
If we simply looked at it and went those are equal and then crossed it out and said 0 through symmetry, would that also be acceptable?
Yeah, 0 by symmetry. Yeah, that would be an acceptable shortcut in this case because, you're acknowledging that, yeah, they're going to cancel each other out and you've looked it over. And if you wanted to, if somebody was demanding that you sub in all those values and really show that it's negative 52 and positive 52, whatever it ends up being, you could do that. Yeah. All right, so the next thing is to deal with the y's. So I'd say, all right, well, epsilon total in the y direction is going to be epsilon 1y plus epsilon 2y. And if I expand those guys out, I've got the kq1 over r1 squared times, last time I used sine theta, so this time I'll use cosine theta, plus kq2 over r2 squared times, again, I should say theta 1 cosine theta 2, consistent with how particular I'm being here. But then again here, if I wanted to do some inspection, I can say, hey, look, by inspection, can you see that Q1 and Q2 are the same magnitude? R1 and R2 are the same magnitude this time. So I can make a little statement here. Q1 equals Q2. Oopsie. R1 equals R2. I don't know why I did the magnitudes on that one, but I did. Still true though. And theta 1 equals theta 2. Still doing magnitudes for no reason. But that means that it's the same thing twice, right? Since k is always a constant. So in the end, I could say, all right, well, maybe I'll just simplify this and say 2 times k q1 over r1 squared times cos theta. So I've made this little statement off to the side here because, again, this is one of those situations where a line like this pops up in a solution manual sometimes. And again, you're like, magic and wizardry. Where did the 2 come from? It's because they've made this recognition of all these identical values, and they're just doubling it. So this isn't like I've derived a new equation. I'm just acknowledging the equality of these things and jump into this line here, okay? So I'm going to ask you guys to take a minute, sub in the values, because clearly by trying to write big and in marker here, I've run out of space. But, so rather than me try to squeeze it all in there, we've got 8.99 times 10 to the power of 9. I've got Q1 and Q2 equaling 1 times 10 to the power of negative 8. I've got R being equal to 3 meters. Oh, incidentally, just because the D value at the top is given as D equals 3.0 meters, that D doesn't mean diameter of a circle. It means distance between 2 points. So please don't like randomly divide it by 2. All right, so the R value is 3.0 meters. Don't get confused. There are no circles here, okay?
Yeah.
Did you do that? You got it all done?
Mhm.
All right. What'd you get?
17.301 newtons per Coulomb down, or 17.
Nice. So we could say down or south based on my reference frame, and we take that to just, I guess, 2 sig figs. So 17 newtons per Coulomb, approximately. South, or whatever you've called the downward direction. Okay, so a little bit of 2 dimensions. Now, based on our workbook, we've run out of pages here, but I do want to bring out one more variation on this. And I think it's going to help with homework. So rather than people struggle through it, I'm going to ask you to pull out a piece of lined paper, if you have an extra piece of lined paper, because I do want to give you like one other twist here, just because I think it's going to help you and save you from feeling like you need to somehow be divinely inspired to solve this problem. Because I find that if I don't do this little talk about this type of problem, I get too many people the next day that come with like anime style question marks above their heads, you know? Can you picture what I'm talking about?
Mm-hmm.
So it's actually over my shoulder, but I'm still going to talk it out here. It happens to be on the whiteboard behind me, but I'm still going to talk it out over here. So we've got 2 charges. I've got a positive charge on the left, a negative charge on the right. And these 2 charges are separated by a distance, d equals 2.0 meters. So that's the distance between them. And then I want to take a look at a point over here somewhere, a point P. And I'd like to know how far away that point would have to be from, we can call this charge 1 and this charge 2. I'd like to know how far away that charge would have to be if charge 1 has got a charge of Q1 and charge 2 has a charge of -5 times Q1. So that's my situation, okay? And I'd like to say, where would that P have to be? And I'll label it as a distance x away from charge 1 in order for there to be 0 electric field there. So as I set this up, maybe I should talk about the electric field orientations. Remember, since this is positive, charge 1, epsilon 1 would be away from charge 1 because of conventions with fields. Epsilon 2 would be toward charge 2, epsilon 2. Again, because of field orientation conventions. So I'm trying to map out what my electric field orientations would be. I mean, it doesn't matter too much which direction is positive or negative. I think I'm just going to make right be positive, left be negative again. It really doesn't matter. But if I want to set up my electric field equation, I'd say electric field total is equal to epsilon 1 plus epsilon 2. Epsilon 1 is going to be the -1, so I'll just put the negative sign in there from the reference frame right away. And then I say, okay, I'll expand out epsilon 1. It would be negative k times q1 over r1 squared plus k times q2 over r2 squared. And at this point, I don't really know r1 and r2, so I'm going to have to figure out how to deal with this with my equation. So I'll say, okay, well, negative k times q1. Instead of writing r1, can you see that it might make more sense to use the variable x? So here's my x. That's how far away point P is away from charge 1. So instead of r1, I'm going to switch it out. I'm going to say x squared. Why I'm doing that will become apparent. Okay, it's not just randomly. Plus k times, you know what? Instead of saying q2, can I write just -5 times q1? By the way, writing one charge in terms of multiples of the other charge makes the math easier in the end. And you'll see that it does, but you wouldn't know that initially, right? So this is, again, like one of those things where it's nice to see it done rather than rely on your own inspiration. And then instead of writing R2, I think it's going to make more sense to call it D plus X. And again, see how D is 2.0 meters? That's the distance between charges. And X is that additional little bit. So D plus X would be the distance from charge 2 all the way to our mystery point, squared. And then while we're at it, if the whole question was, and maybe I should actually write down the question, find the location of P where total electric field equals 0 newtons per coulomb. If that was our goal, I said it out loud, but I didn't put it in writing, then at this point we could probably just put a 0 here. Because that's what the total electric field would be. That's the location we're hunting for, is the location where the electric field is equal to 0. And at this point, I think, wait a minute, one of these values is negative and one of them's positive. Mathematically, maybe I should just take the -1 over. Say, okay, k times q1 over x squared equals k times -5 q1, absolute valued, so it's just going to become positive q1, d plus x squared. And now I think I have to play a canceling game. Because look, there's a k on both sides, so those guys are gone. Divide both sides by k. I've got a q1 that's on both sides, so I'm going to cancel the q1s. And that actually simplifies things a fair bit. So I could say 1 over x squared equals, absolute value of -5 is just 5 over, hey, look at this. Wouldn't this just be d plus x times d plus x, right? And it's not even just d. I said it was 2. Man, I wish I'd written that as 2 meters. Okay, I'll do an extra line of simplification so I can do it. So I can say, all right, how about I cross multiply the 5? I bring the 5 down to the bottom as well. And now I have like 1 over a value and 1 over a value. So I'm just going to invert both sides. Nice, sweet little math trick. So I can say 5x squared is equal to, maybe I'll write it out this way, 2.0 meters plus x times 2.0 meters plus x, and then we do the whole foiling thing. 5x squared equals, 2, okay, 4.0, what's it, meters squared, plus 4.0 meters times x plus x squared. And then if I take that 5x, now I'm just playing math games, right? I take that 5x squared over to the other side. I can say, okay, 0 is equal to negative 4x squared. I'm just trying to get it into standard form while I'm going here. Plus 4.0 meters times x plus 4.0 meters squared. Remember, there's units and variables here, unlike the way you see it in math sometimes. But if I divide both sides by 4, now you know what? I'm going to do, because one of the students in my other class told me that really the math teachers tell us that we should divide everything by negative 4, because somebody somewhere told us that it's just good form to have the a coefficient be positive. And I don't know if I really am supportive of that, but I'll go along with the flow because I'm a conformist. So 0 is equal to positive x squared minus x minus, is that really 1? Minus 1. And then I can just do a quadratic formula to figure out what the x must be equal to. And oh my goodness, if you got out of grade 10 math and you can't solve for that x with quadratic formula, then I don't know what the world is coming to. So I'm going to leave it there, okay? And I think, actually, is there anybody that happens to have the quadratic formula function on their calculator that can just like spit out the answer for this one? Just so we can scratch the itch of people that want to try it on their own. What is it?
No, Hannah did.
Hannah did, but she's not here.
She's now with 1.618 and minus 0.618.
Minus what?
0.618.
Ooh, interesting. So here's the question. Which one is it? How would we know? Yeah.
It has to be positive because distance can't be a negative number.
Oh, I love that. So the answer is we think it must be a positive because the distance can't be a negative number. Sounds
Maybe
good.
It just means the particles aren't actually 2 meters apart.
Yeah, but they are 2 meters apart. They are 2 meters apart. All right. So I think we're gonna leave it there though, and I think that this is going to be helpful for at least one question from tonight's homework and maybe a previous question from a previous homework where you had to find the point in space where there was zero net force. It might help you. Maybe you didn't do that homework yet, but you'll discover it later. Okay.